Hello everyone, today I'm going to talk about translating C code into D code. The why, the how, the tool I made to automate it, and the aftermath of it. So why would you do it? Well, there's a lot of C code out there, a lot more than D code. So when you find examples in documentation or snippets on Stack Overflow, chances are they're written in something like C and not in D. But you still might want to use it in your D projects because the general algorithms or APIs still apply. So the good news is that often with relatively few changes you can turn a C snippet, like on the above, into a D snippet, below. If you're lucky, you don't even have to change anything at all, because the syntax is similar and the features are too. Apart from small code snippets, there's also single-file C libraries. The convenience here is that you simply copy-paste the file into your project and compile it along with your own code, and you got yourself a simple image loader or audio decoder or font rasterizer. And for the same convenience, some of these have been translated to D, and you can find them in the link below in Adam Roop's repository of useful D modules. Going even bigger than that, there's also dub packages, which contain a library which is ported from C, like the ones listed here. I myself have translated a lot of C code as well, going from simple single-file libraries such as the stb Perlin function, the cute PNG decoder and encoder, and the tiny regular expression library, and even some bigger libraries such as the glfw input and windowing library, and the libsound.io audio input and output library. Now, those last two weren't single-file libraries, but it's still useful to have them in D over C, because dub has no support for compiling C libraries currently, and it's hard to configure your dub configuration file to link with a precompiled library or manually compile it as a pre-built command. You can resort to dynamic linking, but it's often clumsy as the user has to have all the right libraries installed on their system, and when they don't, the operating system usually just gives an error message with no further help on how to install it. So often programs are shipped with all the DLLs or .so files they depend on, which kinda defeats the purpose. So you might as well statically link it, but that's very error prone because you're linking object files that have been compiled with different compilers, and you need to make sure that they all have the right settings, like the same target and C runtime library, or else you get a bunch of cryptic linker errors like this, which are annoying to deal with. It would be a lot easier if they were all just compiled with the same compiler. So far, I've been listing reasons regarding to building the code, but there's also the matter of switching legacy code to a modern language to make it easier to maintain. A great example of this is DMD, the decompiler itself, which used to be written in C++, which is like a nickname for technically C++, but it's sticking to the C feature set. After a big manual translation effort, both the front end and back end are now written in D, and many of the digital Mars native compilation tools, as well as their build system Make, have been converted to D as well, even though they were originally written in C. I have linked below a blog post written by Walter Bright about how he converted Make from C to D using better C. That should cover some of the reasons why you want to translate it, but how do you do it? Well, like I said, it's pretty easy because D has familiar syntax and the same features as C, such as the types and operators and statements. And on top of that, it was designed as a successor to C, so if code looks like C and it compiles in D, it acts the same, so there's no subtle differences in integer promotion or operator precedence or anything like that. So to get started, first you need to be familiar with the differences between D and C, and I recommend this great article on the website for that. Then you simply copy the C code, give it a D extension, add extern C on top for linking compatibility, and you edit the file until DMD stops giving you errors, and hopefully then your translation is correct. So what is your approach when you're dealing with a big volume of C code? Walter Bright recommends to do it incrementally. Do it one function at a time, and after translating each function, run the test suite again, and see if it's still green and you didn't accidentally introduce a regression by translating something wrong. You need to resist the urge to fix, refactor, clean up, etc., because those are just ways to introduce new bugs, and at this stage you really don't want to do that. You have to defer this to after the translation is complete and correct. My approach is slightly different. I tend to do it all at once, and once it's finally done, debug the things that were broken during the translation process. This is not per se a better approach, but sometimes you don't have a test suite, and it can also save some time depending on how many things you needed to debug after the translation. It's a bit of a risk-reward situation. I'm not saying this is the better approach, but it is possible and I've had some success with it. Still, don't refactor early, keep the translation as close to the original C code as possible until it's complete. That should cover the high-level approach. Now I want to give you a quick and non-exhaustive list of the changes you're going to make when you're translating C to D. I don't expect you to get all of this in one view, especially if you're not familiar with both languages, but at least I hope it gives an impression of the things that change during translation. So there's a bunch of syntax changes: the arrow operator, the cast operator, the size of operator in D is a property, null is not capitalized, and number literals are a bit stricter in D. Struct declarations are often combined with the typedef in C. In D you don't need to do that, and there's no semicolon after it. And D has more keywords than C, so some C identifiers are not valid in D, and the convention is to fix that by adding an underscore to the end of it. Regarding statements, D has some extra restrictions. Switch statements always need a default case, even if it's just a break. And switch case fallthrough needs to be made explicit with a goToCase statement, unlike C. Using a semicolon for an empty statement is disallowed in D, so you need to use the braces syntax instead. Using an assignment as a condition is not allowed in D because it's often the result of misspelling the equals equals operator. But there is a pattern where you actually want to use assignment as an if condition, and that's when you're checking for an error code returned by a function in one line. To solve this, you can either wrap the assignment in parentheses and add a logic operator after it, or you actually declare the variable inside the if statement, which is a feature D has but C doesn't. But it does require some refactoring. Pointers are a fun one, because in C basically anything goes. You can implicitly convert a function to a function pointer and an array to a pointer, and one pointer can implicitly convert to another pointer type. In D, you need the ampersand operator to take the address of a function, and you can use the .pointer property to take the address of a static array. You can also use the ampersand to get a pointer to a static array, but I prefer .pointer because it also works with slices, and this will come back a few slides down. And in D, there's no implicit pointer cast like in C, so malloc, which returns a void pointer, cannot implicitly convert to a typed pointer. You need to have an explicit cast in D. Basic types are a bit of a mess in C, because you can have, for example, an unsigned short int, but in practice people just abbreviate it unsigned short. And while it's usually 16 bits, it's not guaranteed to be, so there's also a standard guaranteed to be 16-bit uint16t, and people like to have their own variants and aliases of that as well, so you'll also find some other names for it in the wild. In D, just call it ushort. It's a simple 16-bit unsigned integer, consistent on all targets. It is similar for other integral types, though you do need to be careful with long, because D's 8-byte long in C is a long, and a single long in C is only 8 bytes on 64-bit Linux. On other targets, it's 4 bytes. And to get this behavior in D, you need to import the C long from D runtime, like I show below. In C, pointer and array types are written down like expressions. So in this declaration here, it's saying when I index it with something under 3 and then something under 4, I get an int. And if I dereference bar, call it with an integer parameter, and dereference that, I get a char. But this is infamously confusing, so it was changed in D, and their type simply reads from right to left. It's saying x is a static array of 3, static arrays of 4, integers. And bar is a function pointer taking an int and returning a char pointer. If you don't know how to convert between the two, don't worry, stay tuned. In a few slides I'm going to present my tool which will do it for you. Regarding initializers, C99 actually added very expressive structure array initializers with designators, which are names or indices which allow you to initialize fields in any order you want. They are actually more powerful than initializers in D currently, but with named parameters coming up, the gap is closing a bit, so you still cannot take the address of a struct literal. In D you need to make it temporary for that. And also you still need to specify the length of a static array. It cannot be inferred from the initializer. Oh, and you have to spell out type names a lot as well. Now I'm going to go over some of the pitfalls when translating, because there are actually a few exceptions to the rule that if it compiles and it looks the same as C, it acts the same in D. For example, in C, global variables initialize to 0 if you don't give it an initializer, but in D, the float and char types initialize to nan or a bit pattern with all ones. So you need to explicitly initialize them with 0 to make them work the same as C. Local variables in C are uninitialized by default, but D initializes them unless you add equals void. This doesn't make a semantic difference, but it's worth keeping in mind when you want to keep the performance of the original C code, especially when it has large buffers on the stack. C has no name mangling, unlike D, which encodes the module name and types of a function into the function symbol that it exports. Therefore, in C, if I call my function open or init, and someone else calls a function open or init in a different file as well, it will cause a name conflict at link time. Therefore, public functions often have the library name prefixed to it, such as SQLite3open or glfw init. Now, if the function is only used within the C file it's declared in, you can mark it static and it won't be exported in the object file. And D has the static keyword as well, but it's different. It can turn a nested function into a global function, but on a global function it doesn't do anything. You cannot just change it to private either, because despite it being only visible in the module, it's still exported as a public function to the linker. So if it's an extern C function, and I've had this before, then it might be calling the wrong one declared in a different module, which is also an extern C function with the same name. So what you actually need to do is make it extern D in addition to private, so its name gets mangled and there's no conflict with similarly named functions in different modules. Passing static arrays by value. So static arrays are consistently value types in D, but in C, when they are a function parameter, they are passed as a pointer, and so when you modify the function argument, it's modifying the static array that the caller provided. In D, a static array is passed by a copy, so you need to add the ref keyword. Now I want to mention, when I show it in a reduced example like this, it may seem very obvious, but be aware that in actual code it may be a little bit more obfuscated. So this is the code where I actually encountered this translation bug. The static array is hidden behind a type def, it's passed as a static array here, and it's modified right here. Taking the address of a slice is a mistake I made when translating an OpenGL Hello World triangle example from C to D. And I've seen some other people make this exact same mistake as well, because it's very subtle and easy to get wrong. So here I define a global array of vertex data, which I then pass to a function that takes a void pointer and a size parameter. And I take the address of this array, and in C that would just point to these floats. But in D, this is a slice. So taking the address of vertices just creates a pointer to the slice's length pointer pair, and not the actual float data. And similarly, the size of this variable is not the size of these floats, it's just the size of the pointer and length, which is 2 times 8, 16 on 64-bit targets. So when you declare a global array like this, make sure it's a static array by filling in the right length in the brackets. Or pass vertices.ptr and use a vertices.length times float.sizeof instead of vertices.sizeof. Now let's talk about macros. So before C files are compiled, the preprocessor expands textual macros, and D doesn't have it because it's a feature that has turned out to be very bad in many ways. And instead, D has some actual proper features that replace the usages of the C preprocessor. And in this article that I linked, it shows these differences. Here are some easy macros to translate. An include is basically an import or a public import. A define with a constant can be translated as an enum. Define can also be used to create a generic simple function because C doesn't have generics. In D, you can just use a generic function for it. And ifdef is often used for conditional compilation, for which D has the version statements. However, macros can also be used to insert lines of code or even partial code, in which case it's best to just expand them into the thing that they are supposed to deduplicate and live with the duplication for now. Or, if it's at least a complete statement, you can use a string mixin. Now, when the macros are part of a cross-platform API, my advice is to just give up. Expanding them is not going to be cross-platform, and translating them is going to be really difficult, so try to find something equivalent that also already exists. One C library I translated uses stdatomic.h, which provides atomic operations in the form of macros, and there's no easy translation to that to D, so I just converted them to the equivalent in core.atomic. When translating macros, you do need to be careful of side effects, because something might look like it translates to a simple function, but a function evaluates its parameters once and then stores it, while a macro will just repeat the side effects each time you refer to the arguments. So here, expanding sqr with x++ means that the x++ is done twice, while using a function this would just be evaluated once and then passed to the sqr function. So do be careful of that when translating macros. So now you know how to translate C code to D, but when you actually start doing it, you'll quickly find it's very tedious to just make all these changes by hand. Being a programmer, I was obviously looking for ways to make it easier and more automated. I started out by creating some Vim macros to transform C patterns into D patterns. Even though Vim is not my main editor, I thought it was a great opportunity to learn Vim macros and see how far I can get with it. And it did help, but there's only so much you can do with Vim macros before you need to resort to entire Vim scripts. I took a look at dstep, which is a tool that translates C headers into D, and it can translate C types to D, but not inside functions. And also when it encounters something that it doesn't understand, it just quits and prints an error, which I didn't like. I was hoping it could at least translate the parts that it did understand. I started writing a tool using regular expression replacements to translate common C patterns to D, but it didn't scale, and I quickly figured out I really need a C parser to make this work. So I did, and now I'm here to present you my tool, C2D. You can try it here in the browser or run it from dub in your command line. If you go to the browser page, you get a text field on the left, and if you make an edit over here, it will translate it in the text field on the right. So how does it work? Well, it uses a tree-sitter C parser, which has excellent error recovery because it's made for IDEs with autocompletion, and there you're dealing with unfinished code. It does string replacements on the AST nodes and then prints back as close to valid D as possible. I developed it alongside my translation of GLFW, so I would just run the program on one of the C files, inspect the output and look for invalid D and patterns that need to be translated. Then I entered the C code in the tree-sitter playground, which I'm going to show you now. In the tree-sitter playground, you can simply type some code and it will show you the AST it produces. And there you can see exactly which nodes apply to which syntax and what they are called. So that makes it really easy to identify the patterns that you want to translate. And then you just replace those nodes. Now, as I went on, it got more and more advanced. So it's not just textual replacements, but for type translation, it also needs to parse the entire type and reprint it as a D type. And I also got annoyed of adding .pointer to static arrays, but in order to do that automatically, you need to keep track of the types of symbols. So then I added a symbol table and added each declaration I found in it, and if it looked up and found a static array used in an expression, it would add .pointer. And the whole thing actually comes dangerously close to a complete C compiler, but one with a terrible architecture and being kind of not planned out very well. But yeah, I think it does a decent job right now, though of course there are some limitations. Macro translation is very primitive, complex function macros still need to be translated by hand. Also, the parser doesn't act on the preprocessed file because that would lose the information of the defines and such and includes. So it kind of assumes that macros are used in a very well-formed way, and this is not always the case. For example, one common macro is something that specifies the linkage, like glfw API, but the tree-setter parser considers this the return type of glfw func, and it thinks that void is simply an error, and so it will mistranslate this. But despite thinking it's an error, it doesn't give up, it still continues and gives you a best effort translation of the C code into D, which is a nice starting point for your manual touch-ups and fix-ups. Finally, I want to talk about the aftermath of translating C to D, because once the translation is finally done and it's correct, there's still some ways to improve the resulting code by making it more idiomatic D. Examples of this are replacing C-style global enums with namespace enums, like which D has, replacing memcopy and other mem functions with slice operations, which look a lot nicer and are more type safe, replace traditional for loops with for each loops, etc. You can also add attributes to the code. Since it was translated from C, you basically get no throw and add no GC for free because C doesn't have exceptions or the GC. I also like to add pure if I can, but C code does tend to use global variables for error handling, so then you have to refactor global error variables with returned error codes. But the big one is, of course, can we add safe to C code to make it more memory safe? This does require some work. For example, you need to replace C strings and pointer length pairs with slices. Also, unsafe pointer math should be replaced with indices into slices. And one thing I often see in C code is reinventions of dynamic arrays because C doesn't have it. So you have to replace those unsafe calls to malloc and realloc with something that's safe, like the GC or some container library. I made the PNG library translation safe and added fuzz tests, meaning I would give it a PNG with some randomly corrupted bits and see if some of the bounce checks would trip. And guess what? Basically all array index operations were unchecked and unsafe in the original C code. And the checks that were there were using pointer math, which was not robust to overflow, so the checks were insufficient. There was also a case of a pointer pointing into an array, which would become a dangling pointer once the array gets resized, which is a classic problem. And all of this teaches something that we already know. C is not memory safe, and the translation of this library made me experience that firsthand. Closing off, should you translate C to D? It's still a lot of manual work, and when translating a C library that still gets updates, your translation will get behind, unless you maintain it yourself. For example, I translated glfw 3.3.2, but the library is now a few versions further. Well, I'm still happily using my slightly older version of glfw, and if it gets behind too far, I can always switch back to the C library. Plus, DMD can now compile C files with its import C feature, which is still young, but it's still getting a lot of bug fixes. And it means you don't have to keep a translation up to date. So if you just want to make a library easier to build, I recommend using that instead of making a translation. However, when the C code is very small or has very few updates, I would say go for it. Also, if you're the maintainer of the code, or you're going to maintain your own fork of the code, or you convince the original maintainers to maintain the new translation, I would also say go for it. And that concludes my talk. Thank you for watching.